Solubility product constant. That's the topic for this video. And before I get into discussing what solubility product constant is, let's just go back and let's talk about cave systems for just a few minutes. So cave systems are formed out of limestone. Limestone is a rock that is basic by nature in composition. And so when we look at a sketch of how rocks lay, specifically limestone, they form these different layers that you can see. Now, over the course of time, these layers form fractures in the rocks. And so what's interesting about the composition of these rocks is limestone is composed of calcium carbonate. Now, over time, as rain precipitation hits the ground, the water will collect and it'll run and it'll travel through these different regions, these cracks in the rocks. Now, rain is partially acidic because it forms carbonic acid from the CO2 that's in the air. And so over the course of time, what happens is these layers that you see, they start to open up and they'll form these chambers that we see. And sometimes these chambers can be pretty large depending on how long this has taken place. So the chemistry behind this is how these caves form as the water travels down through and it dissolves the surfaces and form these cavities. So it's the equilibrium that tells the story of why this takes place. So when we talk about Ksp, solubility product constant, what we're doing is we're studying the equilibrium that is at play here. In this case, the calcium carbonate forms its own unique equilibrium. Now, calcium carbonate is a solid when you put it in the solution, but that solid does dissolve ever so slightly to form these ions of calcium and carbonate. And so in doing so, it forms this equilibrium, and this equilibrium is expressed by Ksp, the solubility product constant. The solubility product constant is based off the products because the rules say that solids and liquids are not included in expression. So the only thing that's included in expression are the two products here. And we have calcium ions and we have carbonate ions. Now, these equilibriums that form are not going to lie to the right very much. They're going to be mostly to the left. And so we can look at a list of different values that we have for Ksp, and we can find calcium carbonate, which is right here. And what we see here is that the Ksp for calcium carbonate is equal to 4.96 times 10 to the negative 9. It's a very small number, so that means that the concentration of those two ions are very small. One of the things that we can do is we can solve for the molar concentrations of these two ions. So we can solve for the molar concentrations of the ions. This is known as molar solubility. And so the way we do this is we go through the ice chart, as we have seen in past videos in equilibrium. And so that part doesn't change. Alright, well, what is new is just defining molar solubility. Molar solubility is the concentration of the ions. So we're going to use the ice chart and we're going to solve for X. X represents the molar solubility. So Now there's not any initial. This is a solid, so it gets canceled out. So these are 0 to begin with. Plus x, x, plus x, and x. We fill in Ksp is equal to x times x, which is equal to 4.96 times 10 to the minus 9. We want to solve for x, so x is equal to the square root of 4.96 times 10 to the minus 9. And that gives me 7.04 times 10 to the minus 5. So x represents the molar solubility. That means that the concentration of these ions are represented by the coefficients. In this case, they're 1 and 1. So both of those are 7.04 times 10 to the negative 4. If we were to figure out the concentration of the calcium ions, but the molar solubility itself is that. So as we look at this chart here that I've got, and we can just kind of pick a few here. So if we look at calcium phosphate here, we see that the equilibrium constant for it is 2.07 times 10 to the minus 33, which is, kind of reflects back to the fact that it's going to lie very far to the left hand side. So the concentration of those ions should be much smaller than what we calculated with calcium carbonate. And you also pay attention to the coefficients. The coefficients are also going to be different because it's not 1 to 1. It's actually 3 to 2. So 3 moles of calcium to 2 moles of phosphate. We look at, let's say, barium fluoride. All right, barium fluoride has 2.45 times 10 to the minus 5th, but it also has 2 fluorines for every 1 barium. And then if we look down here, another one, calcium fluoride. Calcium fluoride is 1.46 times 10 to the minus 10. It's also 2 fluorines for every 1 mole of calcium. So let's work with the calcium fluoride and let's solve for its molar solubility. Alright, as we get set up here. Alright, so calcium fluoride forms an equilibrium to produce calcium plus 2 fluoride ions. And so, filling in the ice chart here, this is going to go away. This is 0, 0, plus x, x plus 2x, and 2x because of the 2 in the coefficient. So filling in the Ksp is equal to the calcium ions times the fluoride ions squared, which is equal to x times 2x squared. Alright, so the Ksp for that was 1.46 times 10 to the negative 10. So we're going to solve for x here. So we have x, so it's going to be 4x cubed is equal to 1.46 times 10 to the minus 10. Alright, we're going to divide by 4 to begin with, and then we're going to take the cube root of that. So x cubed is equal to 3.65 times 10 minus 11. And then we're going to take the cube root of each side here, and we get x to be equal to 3.32 times 10 to the minus 4 molar. So this represents the molar solubility for calcium fluoride. Now, if you wanted to figure out the concentration of the ions, you would take the 2 times X for the fluorine, because there's 2 moles of fluorine for every 1 mole of calcium. So that's a couple examples on how we solve for the molar solubility of the equilibrium, using the equilibrium constant. So there are some other things that we have to pay attention to, and we have to pay attention to the common ion effect. We need to pay attention to the pH and how the pH is going to affect the equilibrium as well. So, alright, let's talk about 2 effects that could potentially alter the position of the equilibrium with Ksp. The first one is the common ion effect. We've talked about this before, and this is just an application of Shatley's principle, where we study how the concentration of the products are affected, and ultimately that affects the equilibrium's position. And the solubility of a slightly soluble ionic compound is lowered when a second solute that furnishes a common ion is added to the solution. So if we look at the equilibrium that you see here with the silver sulfate, you form the 2 silver ions plus the sulfate ions. Now this naturally forms its own equilibrium, but if you introduce, let's say, sodium sulfate, and let's just give it a concentration of 0.1 molar. Well, now when you go in and you work on the ice chart, before, the concentration of the sulfate ion was 0. It's still 0 for silver because there's nothing introduced, but the sulfate ion here is a common ion in this equilibrium. And so now, instead of the sulfate being 0, it's going to be 0.1. And so you're still going to have plus X here, and in fact it's going to be 2X because of the 2 in front of the silver. And this is going to be plus X here. So you have 0.1 plus X. Now, as you start to work with the equilibrium and you set up the ice chart, what you're going to notice is that you're going to have silver squared times sulfate. So we set this up, we have X, let's see here, we have 2X squared times 0.1, which is equal to the Ksp for that particular solid, and we need to look that up in order to solve for this. So alright, silver sulfate is 1.20 times 10 to the negative 5. So we go through and calculate it. So we divide this out by 0.1. That gives me 2x squared is equal to 1.2 times 10 to the negative 4. 2x squared is basically going to be 4x squared. And so we're going to divide by 4 and then take the square root of that. And we get X to be equal to 0.0055 molar for that solution. So that would be the X initially. If we the next actually X after you added in the 0.1 molar. If we want to solve for X initially, we would go back to the whole process where you have 2x squared times x is equal to 1.2 times 10 to the negative 5. So we'd have 4x cubed. So we would take the cube root of 1.2 times 10 to the negative 5 divided by 4. And that gives me an x value of 0.0144. And this is the initial value. And so this is after you've added in the common ion. So you can see the initial to after is definitely reducing the molar solubility because of the common ion effect. So it lowers the concentration of the ions that are present in solution, and it pushes it to form a solid, and it's going to drive it back to the left based off Le Chatelier's principle. Now another factor that will affect the solubility is pH of a solution. So the solubility of an ionic solute may be greatly affected by pH if an acid-base reaction occurs as the solute dissolves. So this goes back to understanding how the anions are going to take place. So if we had a salt of NaCl versus calcium carbonate, just reviewing for a simple second here. Alright, this is a neutral salt because chlorine comes from hydrochloric acid, which is a strong acid, making this weak, whereas carbonate, calcium carbonate, the carbonate ion, comes from carbonic acid, which is weak, which makes this a strong basic compound. So this salt is basic. So if we were to put an acid or a base into sodium chloride, it would not change its concentration because it's neutral as a salt. However, if we take calcium carbonate and we were adding to HCl or NaOH, the NaOH won't have an effect because it's a basic compound, so bases aren't going to react with bases. But if you add in HCl into a solution that has calcium carbonate, HCl being an acid will neutralize the base and it'll form a solution that's composed of water and a salt. So when you're dealing with salts that are either acidic or basic in nature, then yes, the pH is definitely going to affect its solubility. And the more acid that you put in there, the more likely you're going to dissolve the calcium carbonate completely. So think about your teeth, for example. Your teeth are composed of calcium carbonate. If you drink a Coke and you just let the Coke sit there all day and you never brush your teeth, eventually your teeth are going to rot out. And so that just means that they're going to dissolve over time based off of this reaction that's taking place. So as we look at the Ksp values, we have to pay attention to the equilibrium that's at play. We also have to pay attention to, is there a common ion in the solution, or what type of salt are we working with, and how is the pH going to affect the solubility of that particular salt. Alright, let's look at a couple examples that involve pH and molar solubility. As we were talking about earlier, we stated that the fact that we have a salt that is either acidic or basic, that if you change the pH of the solution, you're going to ultimately affect the solubility of that salt. So we're going to look at this example that involves the iron 3 hydroxide equilibrium that produce iron plus 3 and 3 hydroxides. And so initially we're going to figure out what the concentration is before we add anything into it and ultimately change the pH of the solution. So we're going to look at two different things. We're going to focus on the fact that we have the equilibrium produces iron plus 3 hydroxides. You can see the ice chart is set up. The initial concentrations are 0. You have plus X for the iron plus 3. and you have plus 3x for the 3 hydroxides. So that carries down into what you see here. Now the equilibrium expression for that is Ksp is equal to iron plus 3 times hydroxide to the 3rd power, because it's 3 hydroxides, and the constant was found to be 4 times 10 to the negative 38 mole. So we input the information from the ice chart into the expression. X times 3x cubed is equal to 4 times 10 to the negative 38. And x times 3x cubed simplifies to 20x to the 4th power. So let's get x by itself. So we're going to divide out 27 from both sides. And then we get 1.48 times 10 to the negative 39. To get rid of the 4th root, we need to take the 4th power, we need to take the 4th root. If on your calculator you see that you can't input that into your calculator as a 4th root, you can do it, but there's an alternative way of just putting 1.48, just typing it in this way, times 10 to the negative 39 times rooftop 1 divided by 4 should give you the answer that you see here for x. So this is our starting point. So the x value already is a pretty low concentration, but for the simple fact that the Ksp value is really low to begin with. So now what we're going to do is we're going to add in 0.05 molar NaOH. And so what you're going to observe here is that yes, NaOH is a basic compound, and it also releases hydroxide ions in the solution. So what's happening here is you're going to see that the hydroxide is present in this equilibrium, and as you change the concentration of hydroxide, you're going to affect the pH, and you're also going to affect the molar solubility of this solution. So no longer was our initial concentration for the hydroxide 0, now it's 0.05. So this is definitely going to change our setup in the ice chart. So you can see that we have 0.05 plus 3x. Now going back over here using the equilibrium expression, we're going to input that information into the, and what we get is x times 0.05 to the 3rd power is equal to 4 times negative 38. I go through the process of calculating x, and x is found to be 3.2 times 10 to the negative 34. You see that your initial was 1.96 times 10 minus 10 molar. Now, with the concentration of hydroxide added into it, this common ion here, this causes the concentration to the molar solubility to decrease dramatically, because that just ever so slight common ion effect that you observe happening here. So so does pH affect it? Yes. If we were to add in HCl, well, the chlorine would not react, but the hydrogen ions would react with the hydroxide ions and would form water as a product. And so it based off Le Chatelier's principle, if the HCl is added in, what happens here is it reacts with the hydroxide, and so it actually reduces the concentration of hydroxide, so it leaves a hole in the equilibrium. And so as a result of that hole being left there, we have the equilibrium is going to bump it back up by shifting to the right. And so as the more acid that you add into it, the more likely this solid that's left here is going to eventually go away, because you're going to neutralize all of it. And so that's another example that we could work, but it's right now we're just going to keep it as theoretical. So does pH make a difference? Yes, it makes a difference. Does the common ion effect make a difference? Yes, it does make a difference. So keeping in touch with these two different factors will definitely make a difference in the molar solubility of the salt. Now, there was one other topic that I wanted to kind of cover in this little area, and that is the formation of a complex. So complexes are important to us, and in this particular case, complexes form pretty easily in solution, and it's represented by Kf. Alright, so Kf is just the symbol for formation constant for a complex. And so now we have seen a complex before, and that was with the iron +3 and the SCN- equilibrium. We formed the FeSCN 2+ complex, and if you remember, this was a red blood complex. I don't know why I wrote iron there. Red blood complex, and it formed very favorably. The equilibrium constant for that was 150. Usually the complexes that form have fairly large equilibrium constants as it is. So another example would be copper +2 plus ammonia. When you put ammonia into solution with a copper ion, these react to form a complex. Let's see here. I'll keep my symbol straight here. So this forms this complex here, and this complex has a formation constant of 1.1 times 10 to the 13th power. So you can see that the formation constant is fairly large in its own sense, and so it's going to be lying far to the right of the equilibrium. So these complexes are very favorable in forming, and so they're more likely to form than a precipitate. So the Kc values are directly proportional to Ksp, because Kf is the same for each reaction. And so if we take another example where you have silver reacting with NH3, this silver ion is going to form an equilibrium to produce this complex here, and this complex has a formation constant of 1.6 times 10 to the 7th power. And this is a really favorable complex, and so the equilibrium is going to lie far to the right in this example as well. It's not as favorable as what we saw with the copper and ammonia, but it's still as favorable. And this is so if we were to take a beaker, and in this beaker we place silver ions and chloride ions, what would happen here? It would form a solid of silver chloride on the bottom. Now let's take this same solution and this time we're going to add in ammonia. What will happen is the ammonia will come in here and it will actually break down the silver chloride, because the silver ammonia complex is much more favored than the precipitate itself, because the precipitate itself has a really small Ksp value, but the formation constant is so much larger than the Ksp value. The complex is much favorable, and what eventually happens is it dissolves out that salt and you have the complex form. Once these complexes form, they do not break back down into the respective ions. There's no way to break them down, because the complexes are pretty much permanent in that sense. Once they form, they're going to stay that way for the rest of that solution's time. So as far as this concept that involves KSP and KF, this finalizes that part. So if you guys have any questions or anything, just let me know. And again, all this information is also found in chapter 17 in your textbook. Thanks.